Hello, today we'll study minimal road networks. These problems involve finding the shortest possible network interconnecting a set of points in the Euclidean plane. 2 points may be interconnected by line segments either directly or via other points and line segments. They are known as Steiner's minimal tree problems. Practical applications are in constructing a network of roads which will connect each town to another at a minimum cost, and in circuit boards using gold to connect transistors. First, we shall consider three towns. To simplify matters, let's assume they form the vertices of an equilateral triangle of side 1 unit. At first thought, it might seem that the sides of the triangle with a total length of 3 units would make up the minimal network, but that's not the case. Let's add a point represented by an open circle in a position different from the towns represented by filled circles. Such a point is called a Steiner point. We place it so that the angles between two roads which join this point to the towns is 120 degrees. Then it becomes the centroid of the triangle. The height of the triangle is root 3 upon 2. The centroid theorem states that the centroid is 2/3 of the distance from each vertex to the midpoint of the opposite side. Therefore, the length of each road would be 2/3 times root 3 over 2, which works out to be root 3 over 3. Since there are 3 roads, the network has a total length of 3 times this, and that is root 3, and that approximates to 1.732. So this is an improvement over the 3-unit network previously. We shall prove that this network has minimum length. We construct a triangle PQR enclosing the triangle ABC of the 3 towns such that A, B, and C are the midpoints of triangle PQR. Suppose we shift the Steiner point X to an arbitrary position Y. Then the new network consists of the lines in purple. Viviani's theorem states that the sum of the distances from a point inside an equilateral triangle to the sides of the triangle is equal to the height of the triangle. It doesn't matter where the inside point is. Therefore, the sum of the lengths of the red continuous lines is equal to the sum of the length of the red dashed lines. But each purple line is longer than its adjacent dashed lines because the purple line and the dashed line are sides of a right angle triangle, and this purple line is the hypotenuse. Therefore, the new network, the purple lines, is longer than the old network, the red continuous lines. Therefore, the network using the centroid X is minimal. Let's consider 4 towns. To simplify matters, let's assume they form the vertices of a square of sine 1 unit. It may seem that we can just introduce one Steiner point, as in the previous case, to obtain a minimal network, giving a total length of 2 root 2. That approximates to 2.828. But that is not the case. We can do better by using two Steiner points, so that the angles at these points are again 120 degrees. The total length of this minimal network is 4 times 1 over 3 plus 1 minus 1 over 3. And this works out to be 1 plus root 3, which is approximately 2.732. So this is slightly less than the previous length, 2.828. In general, the number of Steiner points for a minimal network consisting of connecting endpoints does not exceed n minus 2. All such Steiner points are connected to exactly 3 rods, and any two of them has an angle of 120 degrees between them. You find this interesting, and you know people who require tutoring in mathematics to prepare for exams such as this, do call me at this number 012-656-9840. Thank you and have a good day.